Good afternoon. It's great to see you again. After last week absence, I'm sure you are eager for a lot of research study. And here we go. I'm very pleased to introduce Rogerio Soares from Dr. Juan Mures. So Rogerio did his bachelor degree at the Federal University of Pelotas in Brazil. In his bachelor thesis, Rogerio looked into the effects of caffeine on volleyball serve precision. His interest in research drove him into the master program in the same university. He spent 2 years investigating the influence of genotype, physical activity status, and caffeine consumption's level in the blood pressure response to caffeine ingestions and successfully defended his master thesis in 2015. Now, in the same year he received his master degree, Rogerio came to the University of Calgary to pursue his PhD with Dr. Juan Mures in the field of nutrition, metabolism, and genetics. His PhD study involves using the near-infrared spectroscopy, or NIRS, to assess the microvascular responsiveness during hyperglycemia or high blood sugar in healthy and obese individuals. Rogerio plans to defend his PhD next year, and he's on the right track now, with 11 published articles under his belt. After his PhD degree, Rogerio would like to get a postdoc position to continue his PhD research. His ultimate goal is to develop a tool capable of detecting cardiovascular dysfunctions and metabolic inflexibility at the early stage in obese and type 2 diabetes patients, so that early intervention strategy can be formed to help these patients. Now, when he's not working, Rogerio enjoys playing soccer and volleyball. And most people in the lab also knows that Rogerio is a big coffee lover, which explains why his research revolves largely around the topics related to caffeine. Now, please help me to welcome Rogerio with the title of his talk, The Use of Near-Infrared Spectroscopy for Assessment of Muscle Metabolism and Microvascular Responsiveness in Healthy and Diseased Populations. Please.
So thank you, Ikan, for introducing me. Thank you all for coming here and give me this opportunity to explain how we can use this technique and a little bit about my work here at the University of Calgary. So my presentation, as Ikan explained, is going to be about the use of NIRS for assessment of muscle metabolism and microvascular responsiveness in healthy and diseased populations. So these are going to be pretty much the topics of this presentation. So why and how assess vascular responsiveness, the validity of the technique. In the third part, I'm going to talk about my research focus. So why and how assess vascular responsiveness. So first, because cardiovascular disease is considered the leading cause of death worldwide. At the same time, the cardiovascular disease is a highly preventable cause of mortality, and vascular responsiveness at the macro and microvascular levels are highly associated with cardiovascular disease. This is why it's important to measure it. So how is it usually assessed? So the most common technique to assess vascular responsiveness at the conduit arteries level is called flow-mediated dilation. And so this is an ultrasonic technique. And so with the ultrasound probe, you can assess the diameter of in this case, that I'm showing here is at the brachial artery. You can look at different conduit arteries. So in this case, you place the probe in the arm of the subject, in the biceps, and you measure the brachial artery diameter. After that, you inflate a cuff that's placed right below the ultrasound position, and you inflate this cuff for 5 minutes. After the 5 minutes occlusion time, you release the cuff. when you release this cuff, there is going to be an increase in blood flow from here to the forearm and the hand in this direction, and this increase in blood flow is going to increase the shear stress in the vessels, and this increase in shear stress stimulates nitric oxide production and release that stimulates vasodilation in the smooth muscles surrounding the artery. So after cuff release, you record again the size of the vessel. You usually record it for 5 minutes, and you see how was the peak diameter that this vessel reached. Like, for example, in this case, the baseline was 4.5 millimeters, and after cuff release, it reached 5 millimeters now. It vasodilated about 11%, and that's how FMD works. So you'd say like the FMD of this subject was 11%. So the problem is that the FMD technique has some limitations. First, it just works in conduit arteries. You cannot get information downstream microvasculature. So there is a correlation between baseline diameter and percentage FMD. That's a problem with the technique we can discuss in the end of the presentation. But pretty much you can find that the smaller the vessel, the higher the percent of change after cuff release. And again, there is no information on microvascular function. So it's just an upstream measurement. You cannot see the vascular responses within the microvasculature. That's also very important because microvascular dysfunction is an early complication that leads to changes in the whole hemodynamics of the cardiovascular system. So it's very important to detect impairments in the microvasculature. So how can we detect these impairments in microvasculature? The capillaries are very small. How can we see this difference in responsiveness? This is very difficult. So we start applying the near-infrared spectroscopy to look at how this reoxygenation of cuff release was getting to the microvasculature. That is an important component to look at because the most important thing is that you want to see, like, okay, how much oxygen are getting to the muscle. It's important to look at how your vessels are reacting, but how much oxygen is getting to the downstream microvasculature. So how can we apply NIRS to that? So the NIRS system pretty much works like with, it emits lights in 2 different wavelengths. One wavelength is going to be absorbed by the deoxyhemoglobin, the oxygenated hemoglobin, and another wavelength is going to be absorbed by the oxygenated hemoglobin. So based on these 2 concentrations, the NIRS system can give you the deoxyhemoglobin concentration, oxyhemoglobin concentration, total hemoglobin concentration, and oxygen saturation, oxygenation within the microvasculature of the muscle of interest. So this is the NIRS probe that we have in our lab. So you can see that we have like 4 emitters here and 1 receptor. So in this protocol, so how can we measure microvascular responsiveness? So in this protocol, we pretty much repeat the same that FMD protocol. It's pretty much the same protocol. The only difference is that we place, in this case here, we place the cuff right below the knee, and the NIRS over the tibialis anterior muscle. But again, it's important to notice that now we are looking at downstream response. We are looking at the response below the occlusion and at the microvasculature. So yeah, and with the NIRS probe there positioned over the muscle, we can see the oxygenation of the muscle of interest. And this would provide this one of the signal, the most important signal. would provide like a baseline signal of oxygen saturation like this, pretty flat. So again, like the FMD technique, we get a baseline, we record the baseline. It's about 2 minutes, wait till the signal stabilizes. And after this baseline being recorded, we occlude the blood. It's like FMD technique. We occlude the blood flow for 5 minutes, and after 5 minutes, we release the cuff. Exactly the same. And after releasing the cuff, we have this change in the oxygen saturation signal profile. And from these changes in the oxygen saturation signal profile, we can calculate microvascular responsiveness. How? First, we look at this first 10 seconds slope. They call it slope 2. We can see how fast the reoxygenation happens. And we also look at the whole overshoot of reperfusion. So we record the signal for 8 minutes, and you calculate this area under the curve. That's also an indication of microvascular responsiveness. So now that I show why and how assess microvascular responsiveness, we were only like, okay, let's test and let's see if we can detect difference in different populations using this technique that was already found using the FMD technique. So Dr. McLeay, Kate, most of you know her, she was from Juan's lab as well. She showed that slope 2 of reperfusion was correlated to the flow-mediated dilation technique, showing that the faster the slope 2 reperfusion, the higher the percentage in FMD chains. After that, we showed that this slope 2 was also correlated with the area under the curve, showing that the subjects that they showed a faster reperfusion slope here also showed a higher area under the curve. Again, showing that we can detect difference in microvascular responses using the technique. So we decided to, okay, let's look at if NIRS infrared spectroscopy can detect difference in microvascular responses between trained and untrained subjects. So in this study, we showed that the trained subjects show a slope 2, a reperfusion rate that was significantly faster than untrained subjects. And also, the trained subjects show a higher area under the curve when compared to the untrained subjects. Again, pretty clear that trained subjects had a faster and a higher, larger overshoot of this oxygen saturation signal after cuff release, indicating a better microvascular responsiveness. We also test 10 coronary artery disease patients. So we test the effects of 12 weeks of exercise training, a high intensity interval training in the subjects. So we record, we test them like we perform a NIRS VOT pre and post these 12 weeks of training. And you can see that the slope 2 in these patients got really faster after the 12 weeks of training. In the area under the curve, the overshoot area here got really, really larger after the 12 weeks of training, show that this high intensity interval training was very, very efficient in improving microvascular responsiveness in these subjects. So, okay, it was clear for us that, yeah, NIRS VOT technique can detect difference in microvascular responsiveness in different populations. So, okay, is it an interesting tool? Yeah, we discussed like, yeah, that's an interesting tool. So, okay, let's use this tool for my research focus now. That's more related to obesity and impairments in microvascular responsiveness. So in another study, we tested this. We applied this test, the NIRS technique, in lean and obese subjects. So we compared microvascular responsiveness between these two populations. And what you could see is that slope 2 of the obese subjects was significantly slower than the lean control subjects. And also the area under the curve was really smaller when compared to the area under the curve after during reperfusion compared to the lean control groups, indicating that obese subjects have some impairments in the microvasculature as well. So, okay, we look at these profiles between lean and obese, and I have my background, as Inquan explained. My background is I did a master in nutrition, and I'm interested about how nutrients can influence in microvascular responsiveness. And it's already described in the literature that glucose can change vascular responses at the vascular level, at the conduit arteries. But what about the effects of glucose in the microvasculature, and how the microvasculature of the lean subjects and the obese are going to respond to the hyperglycemia challenge? So just a short background is like it's known that postprandial hyperglycemia increase the risk of cardiovascular disease, decrease vascular responsiveness, and is also associated to development of arteriosclerosis. So how could we assess this difference? So what we did, we combined the NIRS technique with oral glucose tolerance tests. So the subjects arrived to the lab. We did a vascular occlusion test with NIRS, and after the first one, that was the pre-one, they ingested 75 grams of glucose. And we test again microvascular responsiveness at 30, 60, 90, and 120 minutes. In this first protocol, we just applied this first protocol in lean subjects at this time to see we could find some difference in lean subjects. That was the first study actually. And what we found that the hyperglycemia changed the microvascular responsiveness, showing a steeper slope 2 at 90 minutes after glucose ingestion. And also the effects of hyperglycemia would be noticed at the area under the curve of reperfusion, the overshoot, that you can see here that the overshoot of reperfusion, the area under the curve, was really smaller at the same time point in lean subjects. In our next study, so we investigate now how this difference in microvascular responses induced by hyperglycemia would be observed in the obese subjects. How are they going to respond to that? So now we test again lean subjects and obese subjects. We repeat the same protocol, and what you can see is that in obese subjects here, the changes in microvascular responses induced by hyperglycemia were more prolonged than in lean subjects. And this difference could also be noticed in the area under the curve. Again, the difference in microvascular response induced by hyperglycemia in obese subjects were more prolonged and sustained for more time here. Okay, this was the microvascular component, like how can we apply this NIRS measurement to examine or investigate difference in microvascular responses using different interventions. But again, when you look at the NIRS signal, we were thinking, and we found some studies in the literature that we can also infer the oxidative metabolism activity of the muscle using the near-infrared spectroscopy. And how? And so during the baseline, during a basal condition, or there is blood flow, the signal here, like in this case, in the baseline, is a balance between blood flow delivery and oxygen extraction. But when you occlude the leg for the 5 minutes, you have no blood flow delivery anymore. And now the changes in the signal here that you can see are reflecting oxygen extraction, oxygen consumption of the muscle. So again, there is no oxygen delivery here. So every change that you see here is just related to oxygen extraction within the muscle. So that was an interesting observation, and that's like, okay, we also know that hyperglycemia or glucose can also change the oxidative metabolism activity. What about if you look at this difference between lean and obese? Because it's to know that the obese subjects, they have a condition called metabolic inflexibility. They have difficulty to change from the glucose to fat metabolism. So let's see how they're gonna react to the hyperglycemia challenge, and how are you gonna observe these changes in the NIRS signal. So in another study, we look at difference in this signal, in the deoxygenation signal, and what you can see here is that in lean control subjects, the hyperglycemia increased the oxidative metabolism activity of this muscle when compared to the pre-glucose ingestion. That's a very interesting observation, because most of the studies looking at difference in oxidative metabolism induced by hyperglycemia or other different nutrients, they are very invasive studies. And actually, you can do that using near-infrared spectroscopy. That's a no-invasive study at all. And what about the obese subjects? So the obese subjects show that completely different profile. You can see that this is the pre-glucose condition, oxygen extraction, and this is 30 and 60 minutes after glucose ingestion. So the oxidative metabolism of the obese subjects didn't increase, and actually showed an opposite response, a decrease in the oxidative metabolism activity of the tibialis anterior muscle during hyperglycemia. And this for us was a clear evidence about the metabolic inflexibility in these subjects. So we still have some ongoing and upcoming NIRS studies. So we have a collaboration with Penn State University, and in December last year, we collect data. So we had a model of endothelial dysfunction where we used like a 20 minutes occlusion instead of 5, and this 20 minutes occlusion is known to induce endothelial dysfunction. And we are comparing how NIRS and FMD signals are going to change, and if the endothelial dysfunction can be observed in the microvasculature as well. And maybe in the next year, beginning of next year, we are going to do another study in collaboration with Penn State University, where we're going to do cause inhibition of COX pathway. COX pathway is a pathway that's involved in pretty much 40% of this vasodilation induced by increasing blood flow. And we also are going to compare this inhibition in, I forgot to put here, in young and old subjects, because old subjects, they have a shift in this pathway, and I can explain later if you are interested. I also just came back from Verona, where we also have a collaboration with University of Verona, and there we test the effects of hyperglycemia on the oxidative metabolism activity and microvascular responses in type 2 diabetes patients, and we are in phase of data analysis and collection. And here, this is going to be my next project. So, okay, we know that these obese individuals, they have this problem when they have to shift from fat to glucose metabolism. So the idea is like we are gonna use the two different kind of exercise models prior to the hyperglycemia challenge. One of them we are gonna use aerobic exercise, so we are gonna increase the fat utilization prior to the hyperglycemia challenge. And using the anaerobic bouts, we are gonna look at if we increase the anaerobic metabolism prior to hyperglycemia, how they are going to respond to the oxidase metabolism instruction. That's pretty much how it's going to work. So they are going to have briefly 3 visits. In the first one, it's just NIRS VOT and the glucose challenge without no exercise. So in the visit number 2, let's say, they would come, we do a NIRS VOT test, and after the pre-test, they do a 30 minutes moderate exercise, glucose, and we test again at 36, 90, and 130 minutes. And then the visit number 3, they are gonna come to the lab, we test the pre-measurements, they do 3 sprints of 20 seconds, glucose ingestion, and we test microvascular response times again at 36, 90, and 120 minutes. So, yeah, that's it. I'd like to thank you, my supervisor, the amazing Dr. Juan Manuel Murias, and my lab group, my advisory committee, Dr. Raylene and Tish, that are supporting me a lot, and the collaborators, Dr. David Proctor from Penn State, Dr. Silvia Pogagri from University of Verona, Dr. Andreas Nies from the University of Tübingen, that we are starting a collaboration as well, and CAPS for supporting me here. That's it. Thank you.
Okay, thank you, Rogerio. The floor is open for questions. Yes.
So, what's the resolution of the NIRS technique? Because in the last class you showed differences in the order of the micromolar concentrations in HHP. So, is this within the resolution of your technique?
Sorry, I couldn't understand.
So, what's the resolution of your technique of NIRS? Because in the last graphs, you showed differences in the order of micromolar, 1, 2 maybe micromolars. So are these differences significant? And are they within the resolution of your technique?
Difference,
And
just
how
let me...
do you measure the resolution of the technique? Like how...
Well, which
how
graph?
sensitive? Like here, there is the gray line and the black line,
Okay.
and the difference is really very small. Even in this one, there is some difference. In the next one, the difference is really in the order of micromolar.
Also,
So what is the resolution? What's the smallest number that you know that you can measure with this technique?
the smaller what? Sorry.
Number that you
Oh.
can measure with NIRS.
The difference that you can measure with this technique.
The smaller numbers.
How accurate is
Like
NIRS in measuring the hemoglobin?
Oh, how accurate.
Yeah, what's the resolution?
Yeah, so actually, to be honest, like I don't understand a lot about the physics behind it. But in this analysis here, we use the area under the curve of the signal to calculate that, and maybe this is why you can see a lot of this. You don't think that the difference is that big, but yeah, I don't know if I could understand very well your question. Sorry.
I would say from the fluctuations within his line tracing there, it's around a micromolar. But that's based upon what I'm extracting from the signal there.
But in the next graph, in the obese animals, the difference is even smaller. So this is what I'm wondering: is this difference significant? Is it within the resolution of the technique?
in the obese animals?
Yeah.
Oh,
She's just saying
oh,
that
the
the actual
Romans,
measured,
yeah.
yeah, the actual measured difference that you're seeing is very, very small, right? It's, when you're looking at that, it's about 27 micromolars to about 25 micromolars. So you're looking at maybe 2 micromolars difference.
Oh, yeah, yeah.
So is NIRS accurate enough to give that a reasonable?
Well,
but in that case, it's not that 2 units difference in the area under the curve, so you have to multiply the
Yeah.
units by the time. So it's a
yeah, you
much
can just
greater
look
value.
at where the signal reach in the end is the whole area under the curve that we calculated.
Okay, Rogerio, let me ask you a very slightly different question in response to what Venus is asking. Have anybody take a blood with a whatever values of non-oxygen saturation level, and then put it into NIRS and see, how much, what is the smallest difference you can detect from NIRS?
I don't know what was the smallest difference, but the NIRS was already compared with real blood concentrations with different. I don't know if that's the question that I didn't.
Yeah, so which means that you have a blood, we know what's the concentrations of the oxygens, right?
Yeah.
Using different technique, and then you apply a NIRS to compare. Okay, if NIRS can produce exactly the same measurements as of other techniques.
Yeah.
People have already done.
Yeah, for sure.
So it was already validated.
Yeah, for sure. Yeah, it was already validated.
I'm just curious, if you wait longer in occlusion, I take it the first part is occlusion,
Mhm.
then, so I'm just wondering, does the bouncing, the reperfusion, does that go further if you had waited longer?
The reperfusion rate here.
Well, yeah, so any of those curves, if you just waited longer and let the curve continue up, or in that case down.
Okay, I can come back to the. Yeah, maybe here you can.
Yeah,
You are
so
saying that
if you wait longer,
wait longer to wait
Right.
to the signal to go
Yeah,
down
so that
further.
keeps going lower,
Mhm.
and then you let go, will it bounce back higher?
So there is a paper from Kate in also my colleague that was one student showing that there are differences like if you occlude the blood flow for 2 minutes, 1 minute, or 3 minutes, and 5 minutes, you're going to see that the 5 minutes produce the faster is low, but if you keep occluding for more time, there is no difference in the slope if you keep occluding for more time. So we think that it goes down. Sometimes after 5 minutes, signal just plateaus, and there is no difference. So it would be like a waste of time to make a occlusion that's 8 minutes or like 10 minutes, and you get the same results. And sometimes the slope starts to get even slower, because I was explained before, like we have this model that 20 minutes occlusion. We have some data I didn't bring it, but 20 minutes occlusion makes the slope very, very slower. So yeah, it makes sense your question, but we tried this before, and after the 5 minutes, it's just like from 5 to 10, let's say, the slope is pretty much the same.
Rogerio, from previous presentation from your group, I remember they were talking about the same equipment, and they were saying that actually the fat tissue can affect the signal. So how did you account for that in your study? So to be able to compare lean population with obese population, because you have a smaller area under the curve, and I'm thinking that maybe can be due to the fat tissue that you have there.
Okay, nice question. But first, if you look at the lean and obese just in this situation, let's say, there is some recommendations. If the adipose tissue is below 20 millimeters, you shouldn't use the NIRS because you are gonna be pretty much measuring adipose tissue. Okay, but that's not the case in this study because our obese population, the BMI was about was about 35, 36, and the adipose tissue there, like we didn't get something higher than 15 or 13 millimeters. And again, this technique is also applied in the tibialis anterior because there, the adipose tissue is very small, like even in obese subjects, and they were pretty healthy, not healthy, they were pretty like young, and yeah, we couldn't see like something, but the amount of adipose tissue like was like higher than 13, 14 millimeters, let's say. And for the metabolic response, it's like a pre and post condition. So I don't know if you were asking about it as well. So yeah, the change in the signal, like it's the same subject in the same day, just pre and post glucose. So if there was some change there, it wasn't related to the adipose tissue because yeah, the adipose tissue didn't change from pre to post glucose ingestion. But it is something that you have to consider. If you are going to test very obese subjects, you should check how much adipose tissue they have in the tibialis anterior. If it's above 20, like you shouldn't test.
I have, I guess, two questions. One is, how long could you occlude the leg before you would do some serious damage to the person?
We didn't test that yet, so it can be our first subject. We're thinking about it, Juan and I. It's like, okay, we should occlude for 1 hour and should the subject lose the limb. Like,
just like ballpark. Like
yeah,
when would problems start to happen?
Yeah, we still don't know. Like using this 20 minutes occlusion, we can see that the response was really bad. But yeah, I don't know if someone is gonna do it. Like I don't know in how can you measure this. Like I have no idea. I have no idea for how long you can sustain an occlusion without a serious damage.
Then the other question I had was, I can understand that a steeper slope is good because you oxygenate the blood faster after the occlusion, and then why is it good to have this big overshoot? Because I would think that as soon as you're back to the baseline, that's kind of what you want.
Yeah, because the idea is not that the faster you come back to baseline, the better your microvascular response. And that actually, this is just a representation of how vasodilated you are. You know what I mean? You have an increasing blood flow here, and you keep this blood flow higher, this reperfusion for a higher amount for a sustain for a longer time. This is just an indication of how vasodilated are your vessels. You know what I mean? I don't know if you.
I have one question.
Okay.
So you look at two different populations, lean population versus obese populations. And I'm sure in your obese population, there are also like a subgroup with some of them are more severe than the rest. Have you compared those groups and see if it is what we use in a basic sense, dose dependent, like the extent of obesity? Does it correlate to what you see here, like the slope changes?
Yeah, we couldn't do that because actually the sample size wasn't that big.
Where's the sample?
We had 13 obese subjects, so we didn't have power to compare it. It was difficult, yeah, with 13 subjects to create a subgroup. It's interesting to do, but yeah.
Yes.
So I'm wondering about the factors that would affect the measurement, like fatigue. If you are fatigued into the lab, or if you are stressed, because this is the vasodilation and the liberation of nitric oxide.
Yeah,
one
of the factors.
Sensitive to all these factors. So I'm taking into account that.
Yeah, what we control was like for pretty much all the measures that we did, we control like for diets, and pretty much all the subjects fast for 12 hours before the tests. And yeah, stress, like it's a kind of different variable to control. And yeah, there was no specific test for stress on that day. So might play a role, but I don't think that was that important in this case, but yeah, it's something to consider.
What are the factors other than nitric oxide that are affecting vasodilation? What are the factors in relation to obesity? The other factors you should be looking at to understand?
The facts that why do you mean the vasodilatory response to? Yeah. So yeah, one of the things like we don't know the effects of occlusion in the obese, in the 5 minutes occlusion in obese and healthy subjects. So maybe this 5 minutes of occlusion in obese subjects can increase the oxidate, the ROS production, and impairs like the eNOS activity and the nitric oxide release and production. So that's one of the causes that we can notice that smaller vasodilation after the reperfusion, during reperfusion. Also, like at least for old, I can remember for obese, but also sometimes the COX pathway, it shifts, like instead you have the PGI2 production, you shift from thromboxane, that's a vasoconstrictor. So, and plus inflammatory markers that are always high in obese subjects may influence in the response as well. I don't know if this is what you're asking.
You had a slide where you calculated some correlation coefficient. Can you go to this slide?
Yep. This one?
Now, if you take the points that you have, your correlation is heavily determined by that point on the top right.
So yeah, we look at.
Do you know anything about that?
So we look at the subjects in all the other variables. They weren't like this. Just they weren't considered an outlier. And just because if you remove them, you have to remove the range here, and you see a change in this distribution, and you can look that the correlation wasn't dependent on these 2 points.
But do you know anything about them? You know, if you take those 2 away, it's not really a correlation anymore. The correlation is very low. So
this correlation here, these 2 exist,
yeah,
actually.
But the question is, do you know something specific about those people that could explain why they are?
Yeah, I can.
The area at the right one is about the double area of the bunch of the data, the quadruple or the double area.
Yeah, I can remember now something related to these subjects, but yeah, maybe something to investigate why they respond that, like they respond this way, like why the slopes were so fast and the other curve was so big, like it was different from the other groups.
I don't think that if you understand the outliers, then you can understand the whole complex better. I would look into that a little bit more deeply.
Yeah.
I have another question. So it's my understanding that your ultimate goal is to detect early intervention strategies so they can help the patients to recover some of their ability to, metabolic ability, these kind of things. And your results show that NIRS can detect small differences. But how big is the difference that will trigger actions from the doctors?
Sorry, how big?
Because you see changes. Okay, you compare lean group and obese group, there are differences. Mm-hmm. But what is the meaningful differences that will put the doctors to say, okay, you have to do something?
Oh, okay, yeah. So that's something that someone asked me before. And yeah, that's still a pretty new technique.
Yeah.
And there is a lot to be tested. So it's difficult to say, okay, this person has this slope, so he has a microvascular dysfunction or something like that. Even because we use the 1 year system, like people in Germany, where we have a collaboration, there is a different year system that gives you some different slopes.
But why is it the same system?
So it's like sometimes it's just the way that the distance between the emitters and the receiver.
Okay.
So it can give you a difference in the whole amplitude of the signal. And so it's still difficult to compare because we are getting like slopes for health controls here, like about 1.6, 1.4. And you can use a different near signal in a different place, a different device, and get a slopes for health subjects that are 2.3. You know? So for now, every time that you want to look at like the effects of intervention, like exercise intervention, compare populations, you have to use the same device.
Okay. So I guess it must be a very new technology. So
Yeah.
everybody has a standardized design.
Yeah.
Right?
Yeah, it would be nice like to have a number to see like, okay, yeah, from this range to this, if you are in this range, you have a disease. If you are not in this range, you are healthy. So yeah, but it's going to take some time. I think.
So since you bring up these things, how do you convince the manufacturer to to stay together, sit in a room and then discuss about a standardized design so that everybody can compare different results? Because what you're saying that is that the design differences can give you different results, which means that every study is unique and it cannot be compared.
Yeah, to be honest, that's the thing so far. Like we cannot, for example, test one group of subjects here, and we shouldn't and use a different device in another place and compare the groups. We are gonna get different slopes. It would be nice if like everybody all the companies talk. Okay, we need to find something that gives you the same values for the same population, but I don't know how long it's gonna take.
So why are they different? Devices in Germany, why are they different than your device? What do they measure differently?
Oh, this is what I just explained to him. Like some device has difference between the emitters and the receivers, and this changes the amplitude of the signal. Further, this device here is one of the best ones. Like we have a calibration block. In other device, there is some different mathematical calculations to do calibrations.
So then what you have here is not really...
What I have here is everybody...
Oxygen saturation, it's some number that you don't know what it means.
No. For this device, we are really confident about it. And another thing is that even that if it doesn't show you oxygen saturation, if it was just a random number, let's say, we work a percent of change actually. When you look at this ratio, we see how fast this number is changing. This is oxygen saturation. The company already tested this device that we use against blood and other different techniques. And even that it wasn't like the real number, we work a percent of change pretty much of in the signal.
I was just going to comment on your question that there's nothing that's not any different from any other medical technology. If you get a DEXA scan on a hologic scanner, you will not get the same bone mineral density as a DEXA scan on a lunar scan. And at the end of the day, probably what will happen if they ever want to sell these things as some kind of clinical device is they're going to have their own databases with T-scores and proprietary information that will spit out an answer. You're good, you're not, you know what I mean? Yeah. So I think at almost everything we deal with these days is the
Which
same.
means that absolute measurement means something nowadays.
No, absolute measurement means something. Yeah. Sorry.
Well,
no,
it's
it's
relative to the interpretation that you make from that machine through consistently.
Yeah, within that machine, yes, I understand that.
Or relative to the interpretations of that machine, where your absolute measurement is consistent.
Yeah. But say I'm doing some great research, very huge research, and someone in Europe wants to compare it and replicate those studies. They couldn't get the same values, mainly because of the device.
Yeah, you always need to have a control group.
Yeah.
And then with a control group, you could probably establish a relationship, and then with that relationship, you could make a valid comparison.
Yeah.
Yes.
But it's still, so far, we still need to have control groups every time that you are testing.
Yeah, so to follow up on this, this reminds me also, I don't want to offend anybody, but of the measurement of EMG of the muscle and trying to correlate what you have in terms of the electrical signal with the force that the muscle is producing. And you know that EMG depends on lots of factors, and then it's just at the surface of the muscle, nothing inside. And so this reminds me of the EMG measurement. So how deep you can measure? Like, do you measure just the surface of the muscle?
Like,
how deep you can go
yeah,
into
like,
the muscle?
exactly, like I said, like this difference in device lock. So the most important thing in terms of the how deep you can measure is the distance between the emitters and the receiver. So usually we calculated how deep you can go is pretty much the half of the distance between the emitter and the receiver. So if the distance is 2 centimeters between them, you are going about 1 centimeter deep in the muscle. So in this device here, we have like 4 emitters, and at 1.5 centimeters, 2.5 and 3 centimeters distance, if I'm not wrong.
You mentioned a lot about the vascular responsiveness. I'm just wondering, like, what does it mean to have a different microvascular responsiveness? Something to do with, like, obviously it's changed O2 uptake and stuff like that. But is it like the end of changing the endothelial cells, or is it changing the fusion? Is it changing the size of the vascular, like microvascular network? What is it that's leading to these changes that you're seeing?
Sorry.
I'm just curious, you've mentioned a lot like microvascular responsiveness and how it's changing. I'm just curious, what does that actually mean? Like anatomically or physiologically, what's going on? Is it changes in endothelial cells? They're changing the fusion rate? Is there changes in the actual size of the microvascular network? If there's increased surface area, you can have increased diffusion. What is actually going on? So you can say the obese, I think, lean versus the trained, what's going on? What are the adaptations that are occurring?
Also, okay, yeah, between training and training, we believe that the increase in the vessel, the conduit arteries, they get larger, and also you have the increasing capitalization, and all these mechanisms together, they facilitate the reperfusion rate when you relieve capital. In obese subjects, I wouldn't say that you have more or less capitalization, but I believe like when you in the situation where you the vessels, like the size of the vessels are smaller, like there are some other factors related to that they cannot vasodilate as fast as the like a lean subject. Like as I told you before, like inflammation markers and changes in the structure, like arteriosclerosis and this kind of things that are associated to obesity. I don't know if this is responded correctly.
Of the tissues that use up the endothelial cells, and then they're also, I assume, angiogenesis will decrease as well, so there will be less microvascular as well. It's like,
could you speak up, please?
I would assume that there'd be less microvascular as well because angiogenesis would be decreased.
Yeah, I don't know about the difference in angiogenesis and obese.
Yeah.
So I can't say that. Like, oh, yeah, yeah, even all the like endothelial function is like the mechanism related to this response. Like they are different in obese because like this shift in the COX pathway. There is other factors like the endothelial. There are hyperpolarization factors. These mechanisms are also changed in these subjects. Very different. So, yeah, I would like to say that this is like what we are measuring, that all these components together. One of the things that we are going to do with this project, first we are going to test young and old, because then use the COX inhibition, because COX is pretty much 30 or 40% responsible for this response, for this dilation, the vasodilatory response during reperfusion. And when you get old, if you usually get like more sedentary, you shift this COX pathway to more into thromboxane direction. That's a vasoconstrictor. So we want to find like if you inhibit this pathway, if this is gonna change the response differently in your compared to your. Because this COX is more
vasodilatory pathway in young, but maybe it's going to be different in old. And probably in the next step, we can repeat this protocol and compare lean and obese, like inhibiting this pathway.
Wait, Rogerio, do you mind to come back here? We couldn't hear you.
Oh, sorry.
Sorry about that. Yeah, go ahead. Sorry, last question and then Vincent's.
The other thing that I was wondering is that you mentioned at the end that you were going to do an exercise intervention, look at like 3 times 20 seconds of like HIIT training, and then you're going to do 1 to 30 minutes of water exercise. How are you normalizing those protocols to, you're going to be able to compare the one versus the other? I could see you compare obese versus lean or whatever, and then you can use those 2 interventions, but how are you going to compare anaerobic versus aerobic if you're not normalizing? How would you normalize that is what I'm wondering.
You mean how can we know if you are in the right intensity?
No, like the 2 protocols, you're comparing you're going to be comparing the vascular responsiveness between the 2 of them.
Mm-hmm.
But what are you using to normalize those 2 different protocols to be able to look at vascular responsiveness? How are you saying that these protocols are equal in relation to, say, oxygen consumption, or what are you saying? How are you normalizing these 2 protocols?
So one thing that we are going to do, I just show like pretty briefly about this research, but we still we are going to do some calculations based in energy expenditure. So I don't know if this is your question. So we went to the aerobic intervention and the anaerobic intervention. I want them to have the same like some energy expenditure. You know what I mean?
Yeah, but then there's also like the epoch following that exercise post oxygen consumption, which is going to change the energy expenditure as well. So if you're just looking at exactly at during that exercise load and matching those energies, then obviously the anaerobic one following is going to be much more taxing energy-wise because there's an exercise post oxygen consumption following it. So I'm just wondering, how do you normalize those 2 protocols?
Yeah.
It's very hard to do.
Yeah, it's pretty difficult. I don't know. I think like at least we are going to try to normalize for energy expenditure, and well, we are going to discuss about the characteristics of 2 exercises. Like they are different exercises. They are going to like change the metabolism in some way. Yeah, that's one part of the thing that we are going to answer actually.
So you said your system is very sensitive to the depth in the muscle. Now when you have the obese person, can you get as close as with a normal person? Is your effect not just an effect of the fat?
Yes, so what I said, like our NIRS probe here, we have like 40 meters that, and the distance between these 40 meters and the receiver like is about, it's between 1.5 and 3.5 centimeters. So if we had a subject that the fat tissue was like layer here over the tibia that they were more than 20 millimeters, we shouldn't test it. But we just had subjects that the higher value was about 13 to 14 millimeters. And also they suggest to do a calculation, a mathematical calculation to correct these values. But in our opinion, it doesn't work because actually it would just shift all the data up, and we work with the amplitude of the signal. We don't work with the numbers. Like for slopes, for example, we see how much percent the slope increase after cuff release per second. And under the curve, we work at a percent of change as well. So yeah, the only solution that they offer now for people that has a huge fat tissue layer there is a mathematical correction that I don't think it's correct for physiological assessment. Yeah.
Okay, I have a question about your approach.
For?
No, it's for Christina. Don't worry, I know the time. So, you mentioned about the conventional technique of measuring the metabolic response being very invasive. but you never talk about how invasive it is. Can you explain to us what is it about the conventional technique that puts the NIRS so attractive?
Yeah, usually if you are going to look at the oxygen metabolism of tissue in the muscle, you need to do a very invasive study, like you have to insert a catheter in the leg, look at changes in the gas exchanges and everything.
And how does your value that you get from NIRS compare to the one that is conventional?
So we look at that, like we compare our studies with other invasive studies, and you look at the difference in time points during hyperglycemia, they match. So when they match, when they found difference in the oxidative metabolism using invasive studies, we can find the same difference using the NIRS systems in the time course response for glucose. Actually, I don't know why I pressed it. This is just some data from Italy, and you can see like in the VO2, the levels of VO2 in the mouth, they increase after the glucose ingestion. And you can see also like that 60 minutes, the RER increases significantly after glucose ingestion. RER is the respiratory exchange ratio. And this shift here indicates that you are now, when you shift from here to here, it's like you are changing your metabolism to a more glycolytic metabolism. You're changing from fat to glucose.
Yeah.
And look what happened in the muscle. This is what happened in the muscle, the leg muscle of 15 subjects, lean subjects and health subjects that we get in Italy at the same point where the RER gets higher, significantly higher, is the first point that we have an increase in significant increase in the oxidative metabolism in your muscle. So we can, in Italy, we also include this analysis to compare what was happening in the whole body to compare with the muscle. Here's the forearm, is another discussion.
Yes.
So then I'm wondering about that, the idea that this is a measure of the size of the vessel. So what you are measuring actually is the amount of oxygen, how much oxygen you get. And so if I have more oxygen, is it necessarily that the vessels are getting big, or there is something else that is changing the flow, the high flow? Is it just the size of the vessel, but you take oxygen more in each for a given amount of time?
You mean at the cuff release time? Yeah. So there are different components. First, it's not just the size of the vessel. So if you have more capillaries, if you can recruit more capillaries during the blood flow occlusion, when you release the cuff. So now this increase in capillarization also is gonna like induce. Yeah.
And so how is it accurate that you're using it as a technique to measure the vasodilation of the vessel?
We know in this technique we don't measure vasodilation. Actually, we measure microvascular response. We measure how fast the oxygen is getting into the muscle, because it would be impossible to look at the microvascular, like how let's say the precapillaries, like how the precapillaries, how much bigger they are getting, or they are. It's very difficult. So I believe so far the only way to look at that is like look at how much oxygen is getting there after cuff release.
I was confused because we're comparing it to the FMT, which is a measure of the size of that.
Yeah. We should markedly show that. Then for sure, like there is an influence of all the conduit arteries in the response, but we still don't know how much the conduit arteries can influence something.
Okay, so my question was related to this question. So you showed the figure in which the slope was correlated to FMT, right?
Mm-hmm.
So based on the result of your study, in subject they had a steeper slope. So can you tell their veins are like more elastic than over the subjects? Because you got more slope in thin subject, right? Which means that they have
It's faster in healthy subjects than in obese.
So it means that the FMD would be higher.
FMD would be higher, yeah.
So
There is a correlation, but yeah, probably it would be higher.
But you cannot tell if the diameter would be, like, the increase in diameter would be higher in the thin subject, right? You cannot conclude that because you don't know how many.
Oh yeah, yeah, I can't conclude that.
Is there any other questions for Rogerio? If not, let's thank him again.
All right, next week, please come back, same time, same place. We have Thea Klansik, a PhD student of Dr. Raylene Reimer, will tell us the effect of early life antibiotic or prebiotic exposure and the obesity risk. I'll see you next week.